This is a revision video about chemically pure substances and formulations, which comes up in the GCSE chemistry topic of chemical analysis. By the end of this video, you should be able to describe what is meant by a pure substance and formulation. You should be able to describe how boiling point data can be used to determine the purity of a substance. You should be able to describe how pure substances can be separated from mixtures, and you should be able to calculate the percentage composition of components in a range of formulations. Talking about pure substances in GCSE chemistry can feel a little bit frustrating, because pure is a word that's already part of your vocabulary. You probably use it all the time already. But then suddenly we're going to come to a chemistry lesson and we're going to say, well, actually that's not pure, and we're going to use the word slightly differently. Now you need to be able to use both an everyday definition and a chemistry definition for your GCSE exams. So let's look at the difference. When you say pure and you're just talking in your everyday language, you might be talking about something like orange juice. And you'd mean that if the orange juice was pure, it's what's come straight from the orange. We haven't added any food colouring or any other sugars or anything like that. We might describe it as being unadulterated. But if you look at this simplified picture that I've put here, you can see that within that orange juice we have water molecules, but we also have sugar molecules and also some vitamin C that I haven't drawn because it's just a bit complicated. So there are lots of different chemicals in there and they're all mixed together. They are a mixture. So as a chemist, I would say that that isn't pure. As a chemist, I would say that in order to be pure, a substance must contain only one element or one compound. So if you look at my second box here, all it contains are water molecules, and therefore it is pure because there is just one compound in there. You need to be able to discuss 5 different physical processes that can be used to separate mixtures. The first of these is filtration, which is used to separate an insoluble solid from a liquid. In filtration, we're going to use a piece of filter paper, usually inside a funnel, and then when you pour your mixture into that, the insoluble solid, because it can't dissolve, it can't go through the filter paper. So it's left on the top as a residue, whereas the liquid is going to go through the filter paper, and we call that the filtrate. If you have a soluble substance like salt or copper sulfate, then filtration is no good because that soluble substance would be able to go through the filter paper along with the liquid that it's dissolved in. So instead we use crystallization. In this, you're going to put your solution into an evaporating basin and then you're going to gently heat it so that the water or other liquid can evaporate, and what's left behind is crystals of the soluble salt that you had in the liquid in the first place. Distillation can be used to separate mixtures of liquids according to their boiling point. So you might have seen certain spirits on them that say that they're double distilled, and this is to do with heating up the mixture of liquids so that some of the water can be removed to make the alcohol stronger. Now we have simple distillation and fractional distillation. In simple distillation, you'd only be trying to separate out 2 different liquids, whereas fractional distillation, we're trying to separate out multiple different liquids. But in each instance, we're basically going to heat up the mixture until one of the liquids evaporates when it reaches its boiling point. Fractional distillation takes place in a fractionating column, which is a very, very long tube with a heat source, something like a furnace, at one end of it. So the mixture of liquids is going to come in and everything is going to be heated up to a very high temperature, and pretty much everything is going to evaporate. As those evaporated gases move up the fractionating column, there's a temperature gradient, which basically just means the further away you are from the furnace, the cooler it gets. As that mixture of gases cools down, the different gases are going to turn back into liquids or condense at different points because they have different boiling points. And so as each one condenses and turns back into a liquid, it can be removed. We talk about this in more detail in Unit 7, which is in Paper 2. Finally is chromatography, which can be used to separate mixtures of liquids such as colours or dyes in order to analyse them. But this is one of the required practicals, so it gets its own entire video, which is the second one in this series. You need to be able to describe different ways of checking whether or not a substance is pure, and one way is by using melting and boiling point data. You should know that a pure element or a pure compound will have a single unchanging melting point and boiling point, and you can look this up in a data table. So for instance, if I look up water, I can find out that pure water boils at 100 degrees. So if a sample boils at a temperature that is not 100 degrees, then it simply isn't pure. But actually there's a little bit more to it than just looking up the melting point or the boiling point in a data table. You should know from your GCSE physics that when you heat a pure substance, we see a characteristically shaped graph. So to begin with, as we heat the substance, the temperature will rise, and then when that substance reaches its melting point, or indeed its boiling point, there will be a part of the graph where the temperature doesn't increase. And the reason for that is that rather than that energy being used to increase the temperature, it's being used to overcome the forces between particles so that that substance can undergo its state change. So we get a graph that looks a bit like this. We have a diagonal line, then a flat portion, then a diagonal line, then a flat portion, and then a diagonal line again. And those horizontal parts of the graph are when the substance is melting and when it's boiling. Now, if we have a substance that isn't pure, then that state change is going to be happening at slightly different times. So we end up with a slightly wonky graph. Maybe something that looks a little bit more like this. The overall shape is similar, but we don't have those flat portions. And this is a key indicator that the substance you're looking at is not pure. A formulation is a mixture designed as a useful product by carefully controlling the quantities of different ingredients that are mixed together. Formulations include lots of really important chemicals, including fuels, cleaning agents, paints, medicines, alloys, fertilisers, and foods. Alloys first came up in Unit 2, but I think they're well worth recapping here. So as you know, an alloy is a mixture where the primary component is a metal. But whereas in a pure metal, we see regular rows of positive ions surrounded by that sea of delocalized electrons, and those regular rows are able to slide over each other really easily, making a pure metal quite malleable. In an alloy, we have particles of different sizes because they're fundamentally different atoms, and therefore the regular rows are distorted and they aren't able to slide over each other. And this makes the alloy much less malleable. In other words, it's harder. Here's an example of a typical exam question about alloys. It includes a maths component and then 2 suggest type questions. Remember, anywhere in the exam that you're asked to suggest, this is something that hasn't been explicitly taught in the specification. You're being asked to use your chemical knowledge and see if you can work out an answer. Pause the video and have a go at these questions now. The first part of this question is assessing how accurately you can read a graph. Now, you can work this out algebraically if you know that pure gold is 24 carats, and therefore working out what proportion the silver is from that, and you'd get an answer of 62.5. But based on this graph, I think we would probably accept anywhere from 62 to 63 because you haven't been given all of the minor grid lines. Now, for some reasons why jewellery tends to be made from 9 carat gold, the obvious one is cost. Gold is pretty expensive, so if we can use silver or copper or something that's a little bit cheaper, then that's going to save us money. Also, the whole point about alloys is that they are harder than pure metals, and pure gold is so soft that it's very easily dented, and that would lead jewellery to being damaged. Finally, we could also talk about intentionally changing the colour of the gold. So for instance, white gold or rose gold are different alloys that have different other metals added to them. Now, again, for the third part, we've got a suggest question. What would happen as we kept adding more and more of these other substances? Well, basically, the gold would get harder and harder, and then eventually it would become brittle, and it wouldn't be very good for anything. The final thing that we're going to look at in this video is percentage composition. As you know, 20% of the marks in GCSE Combined Science are for mathematical skills, and one of the skills that could be assessed is, can you work out a percentage? And this is a really great opportunity to get that in. So here we're given a recipe for a formulation. Remember, that formulation has very precisely controlled amounts of different substances to make a useful product. So here we've got a cold remedy, something like Lemsip, and it contains exactly 1,000 milligrams of paracetamol, exactly 12.2 milligrams of the decongestant that I'm not even going to try and pronounce, and then 500 milligrams of sugar and 487.8 milligrams of some kind of binding ingredients to hold it together. So if I'm asked to work out what the percentage by mass of, say, paracetamol is, I need to know what the mass of that ingredient is and the total mass. So I do a little division and then I multiply by 100% to turn it into a percentage. So in order to work out the total mass, for this question I'm going to need to add up all of these different components, and I get an answer of 2,000 milligrams, which makes my maths for the next bit really straightforward. I'm going to do 1,000 milligrams, the amount of paracetamol, divided by 2,000, times by 100%, and I find out that 50% of the mass of that cold remedy is paracetamol. Percentages are one of those things where the more of these calculations you carry out, the more fluent you'll become and the faster you'll become. So here are 5 questions, and for each one you need to work out the percentage by mass of every single component. Don't forget though, all of your percentages have to add up to be 100. So when you get to the very last one, you don't actually need to work it out in the same way as the others. You could just do 100 to take away the percentages that you've already got. Good luck, I'll be here to go through the answers when you're done. In our cold and flu remedy, we already said that there was 50% paracetamol, but we now know that there's 6.1% of the decongestant, 25% of the sugar, and then if I do those numbers taken away from 100%, I can work out that the binding ingredients make up 18.9%. In this emulsion paint, we've got 25% of that white pigment, titanium dioxide, 45% water, 25% of the binders, and then that leaves 5% for the emulsifiers, which are going to hold the whole thing together and stop it from splitting. In my pancake batter, I've got 19.8% of flour, 0.2% of salt, 21.6% of egg, 36% milk, 13.5% water, and 8.8% butter. Now for this steel, they haven't given us the amount of iron, they've just told us the total mass. So based on that total mass, I can work out that this is 0.95% carbon and 0.9% manganese, and I could then take those away and find out that the iron is going to be 98.15%. And then finally, looking at this petrol, we've got a 50-litre tank. So actually, I suppose in this question, we're doing the percentage by volume rather than by mass. So the 6.5 out of the 50 is going to be 13%, the 15 is going to be 30%, and for the naphthenes, that leaves us with 57%. Thank you very much for watching, and I hope that was a useful introduction to AQA GCSE Chemistry Unit 8. If you did find it useful, then don't forget to like and subscribe for the next video about chromatography coming soon.